and good afternoon to everybody that has just joined us. We're just going to give a couple minutes for everybody to join the meeting, and then we will get started. Good. Okay. Hello, everyone. Welcome to our event, Electrons to Chemicals from Lab to Industry. Thank you for all that have been able to join us today. My name is Erin Scholes. I'm the communications manager for the E2C project that is hosting this event. So I just have a couple slides, just a little bit about how the event will go, and then I will hand it over and we will get started on the content. So here we go. So first of all, we're running the event through Whova. And that's it's a platform that allows us to have a little bit more interaction than your typical Zoom meeting these days. So just some of the functionality that we hope you'll take advantage of. Please look at your profile. You can upload a profile so that other participants can find you and network with you, send you messages, see who else is joining. There's one coffee break during the event where we also have some virtual meetups that you can join and also meet the other attendees and the speakers. Also following the event, there will be a kind of networking session also with these virtual rooms. There's also a community board. You can start discussion topics. You can look into any social groups or find other attendees that might have similar interests. And of course, start your own group if you don't see. And then, of course, I believe there's some PhD students who might be joining us today. So if you need a certificate of attendance, please send me an email. My email address is there, or you can also send me a message through the Whova platform. Oh, excuse me. So during the presentations, we're running this event as a Zoom meeting instead of a webinar. So you are able to unmute your mics and turn on your video. However, please don't do that during the presentation. If you'd like to ask the speakers questions and you would like to do that, just in person instead of typing, you're welcome to do that. Please just use the raise hand function or put in the chat that you would like to ask a question. You're also welcome to submit your questions in the Q&A or the chat. Please do this through the Whova sessions. You can just click on the session, the current session, and put your question there. If you don't get your question answered, feel free to join the virtual meetups with the speakers, or you can even send the speaker a message directly. If that still doesn't work, always feel free to send me an email after the event. And then further, please feel free to use the Whova chat. You can also use if you've opened the Zoom meeting external of Whova, you can also use the chat there, of course. But we're trying to give priority at least to the chats and questions that we see within Whova. Be sure to introduce yourself, put in your email address if you like, let people know who you are and who's attending today. And just to give you a bit more information on how you find these virtual coffee breaks, because this is not always the most obvious thing. So if you're in the Whova app, you can click on the community tab here, and then you'll see this link where you can click on meetups and virtual meets. If you click there, then you'll see these different options. So you can then click on a coffee break, one of the coffee break rooms that you see, and you can hop between them and join conversations as you like. So that's just something, we'll do that for the coffee break and also for the some networking following the end of the event. So now I'm actually going to stop sharing. That was just a brief introduction of the day. And then I would actually like to give it over to Anka Anastasopoulos. Anka is a research scientist at TNO in Delft. She has a background in material science and energy storage research, and she's currently the overall coordinator of the E2C project. And she'll just give a brief introduction of the project. Anka, go ahead.
Yes, thank you very much, Erin, and thank you all for joining us today in this session. So, I'm happy to be introducing you to this event, which is brought to you by the project Electrons to Chemicals, sponsored by Interreg, but also by Smartport and the province of South Holland, the province of North Holland, and the Ministry of Economic Affairs of the Netherlands. A few years back, different parties from the region, which is called E2C, have identified an opportunity to bring power to X technology.
Anka, sorry to interrupt you, but we don't see your slides.
You cannot see my slides. Oh, all right. This is not so handy. Can you see my slides?
Yep, now it's loading. Perfect.
All right.
Great, thanks.
So as I was saying, a few years back, parties from the region of which is called E2C region have come together, and they have decided to bring power to X technologies closer to market readiness in order to contribute to sustainability goals, but also to increase competitiveness for companies in this region. Therefore, a consortium was formed of the parties that you see here from 4 different countries, from UK, from Northern France, Belgium, and the Netherlands. They set out to, as the main objective for the project, to stimulate and support companies to invest in the development of different power to X technologies and to bring innovation to the market. And this is how the project Electrons to Chemicals was born. The project sets out to not only develop technologies, but also develop infrastructure. And this is why we are here today, is to share with you what progress we have done in developing infrastructure for research in power to X technologies, and to share with you also the challenges that we have faced. More specifically, the project develops a lifetime testing station for novel electrolyzer concepts. We are looking at 2 different technology lines, one that we called the direct conversion of CO2 to formic acid, and the indirect conversion of CO2 and hydrogen from electrolysis to dimethyl ether. We are developing and building pilot installations which are meant to be used for research, and also to be used by parties outside of the consortium, and also after the project finishes to do further research in this type of technologies. And last but definitely not least, we are looking at studying the economic feasibilities and even proposing roadmaps for developing these technologies even further. Through this communication events, we want to bring to you the developments that we are achieving through this project. Now, coming back to the event today, we have put together a program that invites both people from outside, and we have two electrochemical specialists that are going to give us a lecture. We have Thijs de Groot, which holds a position at both TUI and Nourion, and Jan Vos from Magneto, special anodes. We have colleagues from the project that are going to discuss technical and non-technical challenges in scaling up this type of technologies. We also want to show you what we have achieved, and because we are meeting online, Erin helped us put together a virtual tour of the electrolyzer test station, and we are also going to show you a video of the field lab industrial electrification. And what I would hope very much from this event is that we are going to network together, that we are going to get your input, and that we are going to get you excited about the work that we are doing, and we can collaborate in the future. So thank you very much for your attention. Back to you, Erin.
Great, thank you, Anke. Good, so I just want to, good. So I will just quickly introduce our first keynote speaker of the day. So Thijs de Groot, as Anke mentioned. So Thijs holds positions as an innovation technologist at Nobian and as an assistant professor at the Technical University of Eindhoven. He leads Nobian's research program on green hydrogen, including the D-Joules project, if I say that correctly, which is realizing a 20 megawatt water electrolysis facility in Delfzijl. At TU Eindhoven, he focuses on the intensification of electrochemical processes. So I will go ahead and give the floor over to Thijs. Thijs, we don't hear you yet.
Oh, yeah.
There we go.
Do you
Perfect.
hear me now? And do you see my screen?
We do see your screen. Thank you.
And you hear me, so that
Yes.
that is great.
So
Yeah,
far, so good.
So far, so good. You never know. I've had some horrible presentations in the past, but at least now at the moment it seems to work. Okay, let me start by sharing some of my experience in scaling up electrolysis. I will do that by bringing in an end user perspective. Here it actually does not say Nourion, but Nobian. Nobian is actually a Nourion company. I'm not going to spend too much time on all the rebranding we do in our organizations, but you can just assume it's more or less the same. So I want to bring a bit of an end user perspective to scaling up, and also basically work with two examples. One example from the past, and one example from a technology in which I'm myself heavily involved in. Okay, now Nobian, we do have quite some expertise in electrochemistry. We have in total almost 1 gigawatt of electrolysis facilities installed, 380 megawatt of chloralkali, 620 megawatt of sodium chlorate production, and 9 megawatt of water electrolysis. Of course, the latter does not sound impressive, still the largest operational in Europe, yet we do have an ambition to strongly grow in that field of water electrolysis. I think it's important to note that except for the sodium chlorate, we are not a producer of electrolyzers ourselves. So that means we go to the market, we ask suppliers if they can deliver us a certain type of electrolyzer according to our wishes. And I think that's also where I basically want to start my presentation. So when you scale up a technology, in the end, you want a customer to buy it. So when a company like we buy an electrolyzer technology, we need to have proof in the field, which means that at least one complete stack has to be running for a couple of years under representative conditions. And that really shows how important it is to have a good demonstration unit, to show how that your electrolyzer process really works. And this is quite a hurdle for a completely new process. On the other hand, if you're just developing a new electrode or a new membrane, and you can basically just put it into an existing electrolyzer, life is much easier, because then we as a company, well, of course, we are not willing to take major risks, but testing a new membrane in a cell is relatively easy. So that makes for easier implementation. So now let's go to some of the key technical aspects when designing an electrochemical plant. Also here, I start with the end user perspective, and that's not technical to begin with. In the beginning, the starting point is always the business case that you have for a new electrochemical technology. The business case relates to sales, capex, capital cost, and operational cost. And these in turn start relating to real technical aspects, like the product specifications, the plant reliability, the footprint, safety, the degradation rate of the process, the efficiency of the process, and the flexibility of the process. And all these are important variables. And often as electrochemists, we tend to focus on DC efficiency, but these other ones sometimes are even more important. Now, if you now take these technical aspects, efficiency, flexibility, stability, you can again translate that to a number of key technical aspects within the stack. And then we're talking overpotential, ohmic resistance, but also gas crossover, shunt currents. It's probably something most of you have never heard of, but it is quite relevant if you start building an electrochemical stacks, that the current actually goes through the stack and not around the stack. Electrode stability and corrosion is really a key aspect. Gas holdup changes are very relevant. Heat management of electrolyzer stacks is a key aspect which you need to take into account when designing your stack. Mechanical strength. So all these topics are relevant. And what is important to note is that often you have to make certain trade-offs. For example, if you make your membrane thinner, it lowers your ohmic resistance, but it can lead to a higher gas crossover, and it can lead to reduced mechanical strength. So there you have a trade-off to make, and that applies to the membrane thickness, but it also applies to the electrode material, whether you take a robust one or a very high fancy material but not very stable. And you have more, like, for example, the operating temperature is a key aspect. Of course, an electrochemical process is much more than just a stack. It is a complete plant in the end, which we need to build, and as a company need to pay. That involves separation processes, compressors, cooling installation, grid connection, and all that. And this is also something important to take into account when designing your process. My focus is on water electrolysis, hydrogen and oxygen, and those are, for example, easy to separate from the product. So that makes that we can still keep the system relatively simple. I think most of your focus is on CO2 electrolyte production, for example, to formic acid. Now, separating formic acid from an electrolyte is not straightforward. And then you have to take into account that you will probably have significant costs also in your system. And that's something you really already have to take into account when designing your electrochemical stack. Now, what I want to do now is just give some examples about processes that one process that has been scaled up in the past. And that's the chlor-alkali process. A beautiful process, of course, since I work for a chlor-alkali company. And here you see, I'm not sure how readable it is. I'm also not going to give you spend a lot of details on it. If it's not readable, then just look at the photo on the right. So basically what I want to say here is 100 years basically in the 20th century, the main chlor-alkali process was the mercury process. And it's quite a fascinating electrochemical process in the sense that you have a liquid cathode, which is not very common. And it was a really nice process, nice and efficient, and proved itself in the 20th century. Now, however, present day, another process is leading, the membrane process. And here you see a schematic of this membrane process. And it basically it's quite similar to, yeah, it's a typical, I would say, flow cell type of electrolyzer. So something has happened in the meantime that has led to the change of the mercury process to the membrane process, and I want to briefly walk with you through that history. Yeah. Because first of all, before you can change a process, most important is that you need certain drivers for change. And there's nothing as strong as a regulatory driver. And often a regulatory driver has set reasons behind it. And in this case, it was a very sad reason. It was the Minamata disease in Japan, which killed almost 2,000 people over the course of 36 years, which was due to methyl mercury in a waste production from acetaldehyde. So it was not a chloralkali plant, but still it was mercury. And you can see how horrific the photos are on the right, that this was really a horrible disease. And yeah, this, of course, in Japan and also around the world, yeah, led politicians to think, well, do we really want significant mercury emissions around us? And basically the answer is, of course, no. So it did lead to strict mercury regulations. Another driver was the energy consumption. You see that the numbers here, that in principle the membrane process can be significantly more efficient than the mercury process. So that is also a good reason to work on that process. But I would clearly say that the first reason here was the main driver for the change towards the membrane process. So these, but of course, you can have a strong driver, but you still need to have a good alternative. And what we saw in the chloralkali process is that there was a nice breakthrough at the end of basically in the 1960s, as a result of the space program, where Nafion membranes were developed, this perfluorosulfonic acid membranes. And these were basically the first membranes that could be stable in a chloralkali type of environment. So with chlorine and caustic and, well, reasonably high temperatures, you need something that's really stable. And Nafion was basically the first membrane that proved itself to be stable. Now, so you had a breakthrough, you had a strong regulatory driver, and then things can go relatively quick. In 1970, they did the first laboratory experiments with Nafion, and in 1972, they already built a pilot plant in Painesville, Ohio. And in 1975, there were already the first, I wouldn't call them commercial, but more demo plants, 10 tons per day, 45 tons per day, 1 to 5 megawatts. So in 5 years, and I think that is really quick, they managed to make this translation from the laboratory to a demo scale. And of course, you can see the photo on the right. This is one of the pilot installations they used back then. Then it continued, and some companies basically took the risk and started building large-scale plants based on this membrane technology. One of them was AXO, which is basically the predecessor of Nobian and Nourion in the field, in our field. And I think we had a very courageous management in 1980 who was willing to build an 80 megawatt plant in Rotterdam in 1980, based on basically because there was a demo unit and they trusted the results of the demo unit. I think it will not have been easy management discussions, but I think everybody is happy that in the end they chose for this new technology. Still, it took until 2017 before the last mercury plants in Europe were closed, and I think there are still some operational around the world, so it shows how long it takes before a technology is truly phased out. What you can also see is that the membrane technology kept developing. You can see that in the picture on the right bottom. And that's basically, once a technology is there, then it becomes easier to improve it. You can put in new membranes, new electrodes, slightly change the cell. Instead, if it's more of a drop-in type of technology, it's easier to implement. One thing I think is also nice to mention, since I think most of you are focused on CO2 electroreduction, is that another nice electrochemical process developed in the field of chloralkali, namely the oxygen depolarized cathode. And in the oxygen depolarized cathode, we don't produce hydrogen on the cathode of the chloralkali process. Instead, we reduce oxygen. And basically, the companies Covestro and ThyssenKrupp have worked on this process for a long time, over 20 years, and have in the end succeeded in achieving this. And by doing oxygen reduction on the cathode, you can save significant amounts of energy on the chloralkali process. The disadvantage is that you don't produce any hydrogen anymore. But what they achieved is to do this on a 3 square meter scale, and basically doing a gas diffusion electrode, making it successfully on a 3 square meter scale is not easy. So I think it's really a very nice piece of chemical engineering that they achieved. The only issue, in my view, is that there's not a strong business driver to implement this technology. We now live in a world where green hydrogen is actually believed to be one of the major players in the energy transition. So then why develop a technology that saves a bit of energy but does not make that green hydrogen? So I think Covestro and ThyssenKrupp will keep struggling to really implement this technology on a large scale. But I want to emphasize how nice it is from a technical perspective what they developed, and that also shows it's a long route. So it also took 20 years to develop this. Now let me bring me to my other example, which is a bit of my own experience. I work in the field of, I basically spent most of my time on alkaline water electrolysis. And my ambition is to intensify that process, because alkaline water electrolysis, if you compare it to other water electrolysis technologies, it's operated at relatively low current densities, and that makes that the electrolyzers are quite bulky, large, and that's not how we want it. So ideally, we would like to achieve higher current densities, maybe not as high as PEM technology, that's, well, at least a factor 3 to 4 higher than what they used to be operated at. Now, I think there is potential to do so by reducing overpotentials, by reducing ohmic resistances. That's not what I want to focus too much today on. I want to focus basically on, what steps do we then need to take to prove it? So because we need, in the laboratory, we need to develop new electrodes, new membranes. And then as a next step, there's still a lot of steps you need to take after that. Because if you have, for example, a new membrane, new electrodes, then you need to test it in a flow cell. Oh, this is a picture of a flow cell. But this flow cell is at atmospheric conditions. Then you need to make it to a pressurized electrolyzer, but this is still small, so you take it to a pilot. And only if you are at the pilot or demo scale, then you can think about taking it to the commercial scale. And of course, in the end, we want to go all the way to the gigawatt scale, because we believe that water electrolysis will play a significant role in the energy transition. So then we're talking gigawatts plants, so maybe even in the future more than a terawatt of installed capacity on the Earth, if you believe the predictions that are currently being made. So really large plans. So we have a lot of scaling up to do in this process. And personally, I'm involved basically in projects around these basically along this complete scaling up line. So let me briefly talk with you about some of the technical and also organizational challenges that I saw in my own experience when doing this type of work. So the first step is you want to move from a 3-electrode type of cell to a flow cell. Well, you already see that the setup becomes more complex. You quickly run into the fact that cell designs, there are hardly any good commercial cell designs out there, so you probably have to make something yourself. And that means, yeah, you have to think about good electrical contact issues with leakages. You have to start thinking about heat management. Is the temperature at which the flow goes into the electrolyzer, is that the same as the temperature going out of the electrolyzer? These are things you have to take into account. It's always more complex than you think. In this step, you still don't have any major organizational issues. You're still fine there. It can still be done in a normal lab environment, so that makes your life relatively easy, and it's also not too expensive. But that quickly changes when you make the next step. If you want a pressurized setup, and typically, ideally, you like to have pressurized electrolysis, especially if you make a gaseous product, like in the case of hydrogen. Then you don't like to produce the hydrogen at 1 bar, you like to produce it at elevated pressures. And that means a lot for your setup. So it means a lot for your material requirements. It means that suddenly you have to start thinking about gas crossover, because gas crossover typically scales rapidly with an increase in pressure. You have to think about automation. So a lot of issues that come on your way when you start scaling towards industrial conditions. Also, it adds a lot of cost, and it takes a long time to build. So you also get into these organizational aspects of such a project. So the first pictures I showed is basically what I'm involved in at the university. But now, yeah, the university can only handle setups up to a certain scale. And if you go larger, you have to go to dedicated environments. So we're working at the Hanse Hogeschool in Groningen. There's a nice, yeah, you could say environment pilot garden where you can put a container and have a nice electrolyzer there. So there we are building now a pilot demo unit, short stack of about more than 50 kilowatt. So the challenges you have there is that you really have to start thinking about the lifetime of your components. So you cannot have it that something is already gone after a couple of days, because you plan to have such a unit operational for a couple of years. You have to think about leak currents when you go to stack, and you have to think about the flexibility of your setups, like ramp rates and minimum load. Costs, of course, go through the roof. You find needs, you already get discussions about permits and things like that. So yeah, there's quite some challenges there. It takes at least 2 years. So, and then after that, you take the step towards the commercial plant. Well, to make it clear, this is not yet with this new intensified alkaline technology, but I just want to show you what is needed. So this is actually a commercial plant of Nouryon, but still with the old technology. So there, the business case becomes leading, and that means that suddenly performance is really important, lifetime is critical, and also reliability. The plant has to operate; it cannot be on and off all the time, and it has to produce the hydrogen at the right specs. So it adds a lot of new constraints. It takes at least 3 years to build, so there are yeah, many new challenges in that aspect from bringing it to the commercial scale. And of course, the last step, coming to the end of my presentation, is on the next step towards a gigawatt scale, which we hope to realize by 2030. Not only us, but many players in the field. So but to realize that, yeah, we actually need innovation. It's not just scaling up the current technology because that's too expensive. So then actually to make these plants affordable, we need cheaper electrolyzers, we need better efficiencies, we need higher current densities, we need cheaper balances of plant. So quite some techno-economic challenges for that one. Costs, they of course go through the roof. Such a plant you cannot build for less than €1 billion. And you need a lot of societal political support to realize that. Well, currently there is a lot of support for these type of ideas, but still to realize them is still a long way. So that's the scaling up of alkaline electrolysis, and well, I just wanted to give you a flavor of what plays in that. So basically the messages I want to give you, well, if you want to move towards a new technology you want to develop, you need strong economic and regulatory drivers to realize it, because otherwise it's not going to happen. It's going to take a lot of time. All these steps take time, and yeah, one way we now try to save time is by basically doing them all in parallel, so that once we make the invention in the lab, so that we can directly test it in these other setups that we then already have available. And it's really important to think how the choices you make on a stack level influence your complete plant in the end. So for example, temperature and pressure at which you plan to operate, that really influences how you make your design. Also the concentration at which you produce your product. If it's too low, you will have a horrible separation train. Okay, and that brings me to the end of my presentation. I always like to close with this picture because it's a bit back to the future or back to the past. This is a water electrolysis plant in Norway, 165 megawatt, which is operational for almost 50 years in the 20th century. And basically this building you see here is not the parking garage. It is the big electrolyzer building that once existed. Unfortunately, it's no longer there, but if you happen to be in the neighborhood, I would really recommend you to go there, because they still have a very nice museum, which even contains some electrolyzers and some nice pictures from the past. And I think we can learn a lot from the past and the scaling up, how they did it back then, because the challenges, they haven't changed. The challenges are still very much the same, and we can save time by learning from what people did in the past. Okay, this is where I would like to conclude. So thank you for your attention.
Great, thank you very much, Thijs. Very interesting. So if anybody has questions, please either type them into the Whova app, or if you're just in the Zoom meeting, feel free to type them in the chat. You're also welcome to unmute and ask a question. If the raise hand function is not working, feel free to also just put a note in the chat that you'd like to ask something. So we have some time for questions. Thijs, I'll start with the first one that I see coming in. It says, why is the commercial plant of 2 megawatts targeted at 1 bar and not at 30 bar as a pilot plant is?
So, and make it clear, the commercial plant is already there. It's a plant of old technology that is already operational for 30 years. So this is not with the new technology. In the end, I think we should build slightly pressurized. But this is a process we still need to do. We have not finished yet with this new high current density pressurized alkaline technology. There is pressurized alkaline technology out there, but the high current density and pressurized is still limited and still needs to go through this scaling up process. So this is just an example of what it should look like when we develop it to that scale.
Great, thank you. And then the next question I have, it says, is it a must to scale up to a centralized gigawatt, or can we build a plan for affordable decentralized megawatt plants?
That's a big debate, the scaling up versus numbering up, centralized for a decentralized. So there are people that claim maybe a decentralized solution with smaller scale can be more effective. I'm not sure myself. Personally, I'm a bit more of a classical chemical engineer that thinks that by scaling up, things become cheaper. So if you scale up a pump, one big pump is cheaper than 10 small ones, and still does the same volume. But there is a debate on basically, if you really make a large number of items, they become much cheaper because of high discounts you have in manufacturing. So it not necessarily has to be a scaled up solution. However, maybe good to mention, what we look at is especially coupling to large offshore wind farms. And these will also be of the scale of a gigawatt. So in that sense, it makes sense to couple a gigawatt scale electrolyzer to a gigawatt scale wind farm.
Great, thank you. And let's see. So I have another question. She says, nice presentation. Says, what I got is just complexity increases with the scale. Is there any recipe that one can follow to make the scale up safer and successful?
No, I think scale just does increase complexity. And I think what you really have to do is just think of all the aspects you have to take into account when scaling up. And therefore, I think in the laboratory, we typically have this tendency to focus on overpotentials and selectivity, and not tend to think so much on all these other things like gas crossover and shunt currents and electrode stability. Maybe we do heat management. It's really important to take these aspects into consideration already at an early stage, because then you basically know whether you're working on an innovation that has potential for success or whether basically is hopeless from the start.
Good. I think that's about all the time we have for questions. Good questions. I thought that's some good discussion points. Great. So thank you very much, Thijs. And again, for everybody in the meeting, please feel free to ask Thijs or send Thijs a message if you want to get into further discussion. Thijs, there might be a couple more questions coming through the chat, so you're welcome to look at those and answer those as we go along. So
yeah,
now,
I'll try to do that. I'm still struggling a bit with IT. No, I don't know if I'm still sharing my screen or not.
No, you're not. You're all good.
Okay, good. Okay, then I'm good. I'll just answer them. Okay.
Great. Thank you very much for being here.
Okay, you're welcome.
Good. So the next thing I want to do is just share a short video that's been made by TNO. Thijs has talked about the electrochemical technologies. But of course, in the project, we have the other side of the CO2 conversion, where you first produce hydrogen and then combine that with CO2. And of course, I can also be connected with CO2 capture. So there's just a short video showing what TNO has been working on. I will just share my screen.
Here at TNO in Petten, we have setups that we use for CWAX and ZMAS development. Let me show you how they work. TNO is active in national and international programs with industry and science to work on technologies to capture and convert carbon dioxide. The biggest challenge for steel, refinery and chemical industries nowadays is to reduce the CO2 emissions while they're still dependent on fossil fuels. Two technologies have been developed. One is called sorption enhanced water gas shift, or CWAX in short, which is a technology where we can capture the CO2 from industrial streams. The second technology, sorption enhanced DME synthesis, or ZMAS, has been developed to convert carbon dioxide into a very useful product, dimethyl ether, or DME. These technologies are cost-effective in reducing carbon dioxide emissions and thereby contribute to achieving the 2050 climate targets. In the north of Sweden, at our partner institute, Sverim, we have a large-scale CWAX setup where we can work with actual steel gas and we can show that the technology is robust. Hydrotelsite is a chemically very robust material because SeaWax operates at 400 degrees centigrade typically and pressures between 20 and 30 bars using high concentrations of steam. Now the SeaWax material is saturated with CO2, and once the material is saturated we go into a regeneration phase where we flush the material with steam and CO2 is removed from the material again. By cycling, we can create a continuous process to remove CO2 from a fuel gas stream.
So sorption-enhanced dimetal ether synthesis, or ZMES, is a novel technology for the direct conversion of CO2 to dimetal ether. Dimetal ether is an alternative fuel or platform chemical. And recently we've demonstrated ZMES at the multi-column test rig here at TNO in Petten. We've achieved up to 95% conversion of CO2 to dimetal ether, and we've shown to be able to regenerate the system with a PSA, so a pressure swing regeneration cycle only, which would allow for faster cycle times and enhanced productivity. Both allow us to scale up the system rapidly.
Dit is de SeaWax 1 reactor. Hij is 2 meter lang, ongeveer inhoud van 2 liter. We vullen de reactor in het geval van SeaWax. Vullen we de reactor met dit soort pellets, hydrotalsiet. We voeden vanaf de top we een gasmengsel met CO2. Wanneer CO2 geabsorbeerd wordt, komt er energie vrij. En we hebben overal in de reactor thermokoppels zitten. Dan kunnen we de temperatuur in het bed volgen. Dus we zien precies wanneer het hele bed verzadigd is met CO2. Dan gaan we de stroomrichting omdraaien. We voeden stoom van onder. En dat stoom zorgt ervoor dat dat CO2 weer uit die pellets geduwd wordt. En we houden een CO2-rijk mengsel over.
This is the SeaWax 7. It's a multi-column system. Like the SeaWax 1 is a single column for batch processes. And here in the multi-column system, we can make a continuous process. So once it's one column is in feed, and another 2 columns are pressure equalization system. The third one is in cleaning mode, in rinse mode or in purge mode. So in that way we can use it in a continuously way. From this year on we use the SeaWax 7 not only for CO2 separation, but also to make high caloric, high value fuels out of it. This is the hydrotelsite, so that's the material for CO2 separation, like a sponge for CO2. And if you add some extra material, some catalyst or other components, and then you can create the reaction to make those high valuable fuels.
In the coming years we will work to further scale up SeaWax technology. The plan is to demonstrate SeaWax in a multi-column unit connected to the steel industry. And for ZMES, we will do field testing in the Rotterdam Field Lab for Industrial Electrification. Are you interested in the background of SeaWax and ZMES technologies? Or are you interested to see applications of SeaWax and ZMES technologies? Visit us at www.tno.nl.
Great. So that was just a short presentation of some of the other scaling activities that are going on at our partners. So now the next item on the agenda is our second keynote presentation of the day. That is from Jan Vos from Magneto Special Anodes. And Jan has a PhD from Leiden University in the group of Mark Kolper, studying the selectivity between the electrochemical evolution of oxygen and chlorine. He joined Magneto Special Anodes in 2020, where his major tasks are the research and development of new electrocatalytic coatings for industrial application. So Jan, I will give it over to you. You're welcome to share your screen.
Thank you, Erin. I'm going to try this exact thing right now.
So far, so good.
Okay, is this working?
Yes, that's working.
Great, great. All right, well, thank you. Good afternoon, and thank you for the introduction, and also thanks for the organizer for making this possible. It's really nice to see all the activity and initiative that's going on in the CO2 reduction research sphere, and it's actually also nice to see a few familiar faces. Well, I am aware that the motive of this conference is about scale up from lab to large scale, But I also want to note that I myself have only been working for Magneto a relatively short time. So my research activities has been mainly about trying very new things. So in short, I look forward to the day when scale up of my activities will come, but it has not arrived yet. As a matter of fact, actually a couple of years ago, we had an interesting, an actual case study of scaling up concerning a chromium plating application, which we developed in tight cooperation with our client. But unfortunately, at this time, I am not able to share anything about that, but maybe in the near future, it will be possible. So I will use this opportunity to tell a little bit the story of Magneto, the business. And through this, I will also give you a perspective on the electrochemical industry from the anode side of things. So electrochemical processes where the focus, or at least where the research focus is on fabricating the anode. So yeah, that also means that in our company, we are not directly involved in CO2 reduction, but obviously to have a functioning electrochemical cell, you still need an anode. So in this way, it's still relevant, I think, to learn a little bit about what happens on the oxidation side of the cell and how the oxidation reaction is applied throughout other electrochemical industries. Now, a very brief history about Magneto Special Anodes. We are the company, more or less officially, that actually invented titanium-based anodes. This invention was done by Dr. Henry Beer, shown here on the right. And in 1965, he invented the production of a ruthenium-titanium mixed oxide coating onto titanium. This is actually the basis of chlorine evolving anodes that are used in the chlor-alkali industry. And it's this patent that it's based on is sometimes called the Beer 1, and it's actually considered to be one of the most successful electrochemical inventions of all time. So it was really quite a remarkable achievement that he did back there. In 1967, he improved it a bit further by finding the optimal ratio between the metals in the mixed oxide, and this is sometimes called the Beer 2 in our walkways. Ever since, as Magneto, we've grown as a company, and nowadays we offer a multitude of different coatings and configurations, which are mostly, again, mixed metal oxides, or as we call them, MMO coatings. So we've been busy, we've been active for quite some time. Since 2016, we were acquired by Evoqua Water Technologies, which is a global water treatment company, and we've fit in quite well there. So in Magneto, as the name implies, we design and we produce titanium-based anodes. One of our core focuses is also, as the name implies, specialization. So we really, our work method is really to collaborate and intensively work together with our clients to find the right anode coating for them and to optimize it further over the course of use. And the anodes that we make, they come in many shapes and sizes. And this is, of course, very heavily dependent on the customer's specific wishes and their needs. Our coatings are usually based on precious metals, such as iridium, ruthenium, and platinum, or mixtures of these. And we have 2 plants globally in the world. One of them is in Schiedam in the Netherlands. That's where I work. And the other one is in Suzhou in China, where we have another plant that's, both of these plants are focused on fabricating anodes for their local relevant market segments, which I will get into in a moment. But both of the research teams collaborate on a very regular scale. Now, in this next part of my talk, I will give you a very short overview of the electrochemical markets that we serve as Magneto. So this is probably not an exhaustive treatment of the entire anode electrochemical market, but we are in many markets, so it's arguably quite close. The only 2 big markets that we are not involved in are chlor-alkali and the fabrication of aluminum. But otherwise, we are quite involved in many markets. So the first one I will briefly talk about is metal plating. So that involves either coating some substrate with either a thin layer of metal or more bulky layers. First of all, there is the plating of copper. This can be either for fabricating copper foil, which is, for example, used in car batteries. There is also the fabrication of printed circuit boards, which are also made using copper. In the case of copper foil, you need a stable anode that has a homogeneous current output. And in the case of the PCB, you also need a stable anode, but this time with a low additive consumption. So both of these processes are actually very harsh. They have current density regimes that are irregular and are very demanding, with an acidic electrolyte and with peak currents that can sometimes increase more than 10 to 50 amps per square centimeter. And then it also involves current reversal at times. So it's a very nasty, demanding application, both of them. So yeah, the anode has to be very well tweaked to withstand these conditions and be able to survive the process itself. These two processes, these two applications are mostly researched and developed by our colleagues in China, because that's where the majority of the production of these components happens nowadays. Another industry that we are more closely involved in is steel strip plating, with the purpose of increasing the corrosion resistance of steel, which can be done either through electrogalvanizing, tinning, or electrochromium plating, as we call them EGL, ETL, and ECL. In each of those, you either deposit zinc, tin, or chromium. ECL was actually a relatively novel process. That's the case study that I mentioned before, but hopefully in the future I'll be able to share some more details for those interested. So in all of these processes, just like the copper process, the plating process is actually what's of interest, and our anodes play the role as current supplier. So to complete the circuit, of course, you need an oxidation reaction, and the oxidation reaction takes place in our anode and is usually the evolution of oxygen from water, so water oxidation. The conditions in metal plating and steel strip plating are a bit more mild than copper plating, but not by much. So that means you will still need an iridium-based MMO to supply the current to this process without dissolving everything. Another application that's slightly related to this is metal winning, which is where the metal of interest is electrodeposited in rather bulky films on the cathode after they have been extracted from either mineral ores or scraps, where the goal is to isolate this metal from the mixture in a very pure way and then process it further or sell it. Again, the desired counter reaction here is oxygen evolution, which again, considering the usually quite acidic conditions of this process, means that you will need iridium. In this picture on the right, this was taken at the Vale nickel winning electroplant in Canada. You can see the many rows of cells here. So in this plant, there are several thousands of our anodes in use, which are all coated titanium plates. I will now move on to a field which is very different from metal plating, and I think is highly interesting because it's absolutely crucial to our society, but it also typically operates very much under the radar, and this is cathodic protection, or in the case of Magneto, the more specific market within cathodic protection, which is called impressed current cathodic protection, or ICCP. So cathodic protection is used to protect any kind of steel structure from corrosion over the course of time. And when I say the course of time, I mean typically tens of years. So it's a very long time when this process is needed. So I will take some time to explain the principle behind ICCP. So of course, a great many structures are made from steel, which is either bulk steel, but you should also think of the steel support that is used in reinforced concrete. And as we know, steel is easily corroded because iron is not quite the most noble of metals, as you can see in this equation. The thermodynamic driving force for steel corrosion is from the reaction with atmospheric oxygen, which like to be reduced to water. And with no precautions, that means if you look at the reaction potentials, equilibrium potentials, any steel structure that comes in contact with air will spontaneously corrode, and it will slowly lose its integrity because of iron dissolution and rusting. Now, what is actually done in ICCP is that the structure is hooked up once again to a titanium-based mixed metal oxide anode or some other anode. And then a current is impressed by using an external power source. And in this way, you basically turn the steel structure into a giant cathode. And with the external power source, you apply a potential very precisely such that the structure is no longer a galvanic cell. So to achieve this, the potential or the impressed current is tweaked so that only the cathodic reaction on the only cathodic reaction on the steel structure is oxygen reduction, and that the iron dissolution reaction is completely stopped. So to illustrate this a bit further, I want to discuss this figure. So corrosion, which is of course what happens to iron here, is a kinetic phenomenon, and it involves mixed potentials. So what this means is that when the structure is left to be without any external driving force in the atmosphere, you will have two reactions that dominate on the surface, which are, as mentioned, oxygen reduction, which is this curve shown here, and iron oxidation, the iron dissolution curve shown over here. And under spontaneous conditions, the system will then approach a potential called the corrosion potential, where the current due to oxygen reduction and that due to iron oxidation exactly match, so that the net current is zero. This is the natural state that the system likes to be in, and under this state, iron is actively corroding. Now, to prevent this from happening, a potential is applied to move the potential of the structure towards a protection, a potential where the whole structure is protected. So the potential is tweaked such that it is at this area where the iron oxidation curve intersects with the iron deposition curve. And exactly at this point, the iron surface of the structure becomes completely inert. Nothing happens anymore, and at that point, the structure is cathodically protected. To achieve this potential, you still need to have some kind of oxidation current to maintain this electrode, but instead of this oxidation current coming from iron, it is now coming from the titanium iridium MMO. And all the current is localized on this MMO. So the MMO basically takes over the role of oxidation sink from the iron, protecting the structure. Now you can also do this with the so-called sacrificial anode, but the advantage of using an ICCP approach is that you have a much longer lifetime, typically many decades. You need fewer anodes, and you can also actually tweak the applied potential as is required according to the specific conditions. So as you can imagine, steel structures are everywhere, which means they also need protection everywhere. They can be protected on sea, such as these wind turbines, or ships are commonly cathodically protected. On land, you can think of pipelines. You can also think of, again, concrete structures. Boilers are another interesting application, I think, that are widespread, both in houses, but also in industry, where cathodic protection is applied to protect the inside of the boiler. And interestingly enough, I do not know to what extent this is true, but it is said that the delta works in the Netherlands, so the stormvloedkering and the Maaslandkering, the structures that protect us from severe water surges during storms, well, these are also cathodically protected and partially by us. So we're doing a good job. We're saving the country. Now, a third interesting segment in the anode world of things is electrochemical water treatment. Then you need to think of applications such as disinfection or electrochlorination, the fabrication of potable drinkable water, swimming pools, treatment of swimming pools, and the treatment of cooling and ballast water. Another related application is the treatment of wastewater to neutralize contaminants and poisons in the water, and also the fabrication, the manufacturing of ultra pure water, such as in Millicu machines. Millipore, who make these machines, has been a good client of us for quite a while. So for the researchers among us, there is actually a chance that one of your Millicu machines is using anodes that were made by us in our factory. Now in water treatment, interestingly, the intended reaction is not oxygen evolution, but chlorine evolution, with the end goal of producing hypochlorite, which is the actual water treatment agent. So chloride is first oxidized to chlorine on the anode. The chlorine then dissociates in the water as hypochlorous acid or hypochlorite. And this is a powerful oxidizer which will react to any nasty organic in the water, and it will destroy it and neutralize it. On the cathode, you generally have the counter reaction, which is just the formation of hydrogen from water. Now, this is an interesting segue into this new market, which is obviously, you might recognize this picture from Thijs's presentation previously. So the new market for us at Magneto especially is water electrolysis for hydrogen production. So with the explicit goal of producing hydrogen. At this time, the hydrogen market is still relatively small, but as Thijs pointed out, the interest in hydrogen currently is very large. Interest in hydrogen has come and gone by waves, but this time we feel it's quite different. In part of the Paris Accord and also in the higher urgency surrounding climate change. So we believe that this time the interest in hydrogen will be a lot more permanent than it was in the previous waves. There are many global and also localized in the EU initiatives and also many interested end users. The interest is growing quite substantially. Of course, in water electrolysis, you have the alkaline and the acidic approach. Within Magneto, due to the nature of our markets, we are used to working with mostly acid or neutral applications. So acidic electrolysis would be our, if you will, natural way to go. But we also believe that in the end, it will be alkaline electrolysis that will dominate the market, simply because the absolutely crucial component of iridium is simply too rare to sustain large-scale acidic electrolysis. So at Magneto, we have also started to investigate nickel-based and PGM-free anodes for water splitting. We are also currently collaborating with TNO, also in the framework of acidic electrolysis, of improving the properties of porous titanium for the use in these kind of electrolyzers. So in this project, we have studied several types of titanium, porous titanium so far, such as felts, shown here, which are interspun wires, and sintered materials, which are tiny pellets of titanium pressed together. And we're trying to modify these structures into making a better component for the acidic electrolyzer technology. So this brings me to the final part of my presentation. As a research team within Magneto, what do we do? And also more general for industry, what would be the priorities? Well, of course, we want our anodes to be of the best performance. And yeah, performance we ideally measure as with 3 criteria, being activity, selectivity, and above all, lifetime, where cost is always, as its business, is the driving factor. In terms of analysis, the study of anode coatings is our core business, of course. Fabricating and then analyzing these coatings is what we do. So the study of these anode coatings is part material science, part electrochemistry, and part purely black magic. As you can see, the thickness of industrial coatings is usually in the order of micrometers, not just ours, but also generally our competitors. And we have a fully equipped lab for doing these studies. Both in Schiedam and Suzhou in China, we have a proper lab for doing proper experiments. And the techniques that we usually use in the lab is, from the materials perspective, we look a lot into roughness and composition of the coatings using X-ray fluorescence spectroscopy. We also do more detailed investigations for structure activity relationships using SEM and FIB, focused ion beam. And we generally also do a lot of adhesion tests for these coatings. We also, for the electrochemical part of things, have a proper electrochemical setup where we do the very typical experiments such as voltammetry, Tafel analysis, and impedance. And of course, we also look at selectivity using some supplemental techniques. And another thing that is extremely important is durability, for which we have a large capacity of testing. We have many different cells where we can test different samples in parallel, where we have roughly 100 channels to do this. So in my second to last slide, there's a few personal notes that I have found when going from the lab to real life, especially going from an academic lab to real life. And that is the first one, which was also emphasized by Thijs, is that activity is usually much less important than lifetime. Lifetime is the most important parameter of all. When you're fabricating catalysts, furthermore, I also typically find that the more complex a procedure is for making something, the less attractive it becomes as soon as you go to large scale. There's all these beautiful academic papers about very intricate structures and steps, but this is completely useless to industry. If your process also requires toxic or hard to obtain precursors, or such as precursors that only have a single supplier, that's also extremely unattractive. Another thing that is found is, for example, a very mundane but important thing. Coatings must be foolproof and they must be scratch resistant, because when you supply an anode to someone, it will drop. Someone might drop it on the floor, it'll get damaged. It needs to be resistant to that. Yeah, there are a lot of complex things when going from trying to emulate a real application in the lab. It's always difficult. And this is also coupled to detrimental conditions that are completely outside of your control, but which may very well affect the performance that your customer records, such as problems in their setup, uneven polarization, problems with mass transport, or contaminants in the electrolyte. It's quite tricky sometimes. And another important note is that the industry is usually conservative. So if you have a wild idea, you still need to have a very good case to get them to move, basically. So above all, you need to accept the many unknowns that come with industrial research, because sometimes the answers are simply not there and you have to make a good shot in the dark. So with that, my take-home messages are that I've hopefully convinced you that titanium-based anodes are an important component of many industries, and that they could be key enablers in the energy transition. Well, they already are, but they could be even more. They could also actually be a suitable counter-electrode for CO2 reduction. And I've also talked a bit about our collaboration with partners, and that has given us much valuable information about how our coatings work and how to improve them. And we think that's a very important thing to keep doing. Keep collaborating with your end user. So with that, I thank you for listening. If you have any questions, please let me know. And of course, if you need a specific anode for your application, you're welcome to ask about that as well. This concludes my presentation.
Great, thank you very much, Jan. So for everybody joining, please drop your questions either in the Zoom chat or in the Whova Q&A. We do have a couple questions coming through already, Jan. So the first one I would like to pose to you: if you don't use sacrificial electrode materials, do you have to put energy in the system continuously? And if yes, how much?
Yes, you indeed have to do this, but the energy requirement is generally quite low, because only a very tiny current is required to maintain the required potential.
Okay, great. Another question for you. Do you also look into non-precious metals such as nickel, iron, cobalt, that we see good performance in the last decade?
Yeah, this is, for me personally, actually one of the major projects that we are working right now. And in this research, we are trying to go beyond the nickel mesh or the nickel plate kind of approach. We're really trying to develop something that is better, while still preserving a high lifetime.
Okay, great. And another one here for you. What is a reasonable payback time for the electrodes for water applications?
That's a question I will gladly refer to our sales department. But if you want to, if you can send this question to me privately, then I can forward it to those that yeah, I can forward it for you.
Okay, great. Sounds good. So let me just look here if we have any other. And we still have a few minutes if anyone wants to drop questions in. Oh, here's one coming through. What is the difference between the standard noble metal counter electrodes and titanium coated electrodes?
What exactly do you mean with the standard noble electrodes?
For CO2 electro reduction.
Ah, okay. Well, I guess what kind of electrodes are normally used there? Is that platinum maybe, or?
I believe so. I don't know if anybody from the E2C project can confirm. Yeah, I see a comment coming in that yes, that's confirmed. Lately,
It's
people
mainly-
use nickel mesh or nickel foam as well.
Right. Yeah, I guess the main advantage would be that the titanium-based anodes are more stable in the long run. So that means they will release less contaminants in the electrolyte, and they will probably also be able to uphold the cell potential for longer.
Okay, great. Do we have any other last minute questions coming in? And feel free to unmute and ask a question if you prefer that than typing. Okay, here's one coming in. I was wondering which method is used to create the titanium coating?
We generally use thermal decomposition methods along with sputtering methods. Sometimes a mixture of these. Yeah, I cannot disclose you the full details of this, of course, unfortunately, because it's a trade secret. But it's generally, yeah, it's a mixture of thermal decomposition, sputtering, and also electrodeposition. But yeah, with these things, the devil is always in the details. You can know how to thermally decompose something, but to do it in the precise way that you get a functioning anode, that's the secret of the well, the secret of the craftsman. Let's call it that.
Good. Any other questions coming in?
I would have a question. I'm curious, Jan. At which scale do you produce these electrodes? Typically, let's say, which is the largest scale that you would have?
Yeah, this to give you a unified answer on that is a bit tricky. It really depends on the customer. We have customers that only want like thumb-sized plates or rods, for example, like for the protection of household boilers, as I mentioned. We have customers that use wire for cathodic protection, and then they want several kilometers of wire. We have customers that, as I showed you with the nickel electrowinning plant, that need thousands of plates, which are square meter size roughly. So yeah, it really depends on the client and their needs. We also collaborate with the universities, and then they just need maybe 4 or 5 small plates.
Thank you.
Great, I'll give one more second for any last minute questions. Okay, great. Then Jan, thank you very much. It's a very interesting presentation. Good. So then just to move on, I just have another short video that we'd like to share with you because of course today we're talking about scaling up and piloting. And sometimes we have the question of how and where and you know, how much will that cost? So there's an initiative going on in Rotterdam called the Field Lab for Industrial Electrification. So it's a short video, and after that we will break for a coffee break.
CO2 reduction through industrial innovation with Power 2X. The case for a field lab industrial electrification. Rotterdam Moerdijk faces climate and socio-economic challenges because of fossil fuel dependency. New technologies and organizational structures are needed to remain competitive and survive in the long term. The region has to keep a license to operate and participate in new industry to secure economic competitiveness. With increasing production of renewable energy, industrial electrification, through power to heat and power to chemicals, is a promising option. The Rotterdam Moerdijk region, as world port, is in a unique geographical position, because of existing infrastructure, the proximity to green energy sources, and diversity of companies. The field lab will accelerate technology development, applicable for the whole industrial cluster. This center will enable development and demonstration of technology, and provide a platform for parties to cooperate, creating new generation electrochemical processes. Upscaling at on-site locations will accelerate adoption. Bronswerk developed an industrial heat pump, which now needs to be scaled up. Hydrogenius Technologies has developed a system which facilitates easier transportation of hydrogen. This technology is available as a containerized solution, but has also been developed for industrial scale. Howden develops compressors for large industrial heat pumps, as well as hydrogen compressors for hydrogen storage. Galen has developed a dryer which runs solely on electricity instead of natural gas. Dyker has developed hydrogen and ammoniac burners for industrial application, with low NOx emissions. Stork has developed hybrid boilers, which use electricity, and gas, and hydrogen in the future. To test, develop and implement these new technologies, we will need your support. Our field lab will be the playground for the industry to test electrification technologies and business cases.
Great. So thank you all for joining so far. So now we have a coffee break going on. We'll resume the sessions in about 25 minutes. So at 3:20. And I hope to see you all back then. Please be sure to join the virtual meetups through the community tab, as I mentioned before. We hope to have some good discussions there. We'll see everyone soon. Great, welcome back everyone. Soraya, do you hear me okay?
Yes, now I can hear
okay,
you.
Now you hear me, okay.
In the network session, the sound was a bit of a problem.
Yeah.
First I didn't hear you, and then I heard myself and Katie echoing, and then it wouldn't stop. But now I think it's all good. If you can hear me, I can hear you.
Yeah, I can hear you.
Good news.
Yes, definitely.
Shall I start sharing the screen? Oh, you will first do a brief introduction.
I will just give you a brief introduction. People are still joining in, but let's go ahead and get started so that we stay nicely on time. So welcome back, everybody. I hope everybody had a good coffee break. So our next speaker is Soraya Slaughter from TNO. Soraya has a PhD in organometallic chemistry and catalysis from the University of Amsterdam, and she is now a project manager at TNO in the Netherlands. For a team developing technologies such as the sorption enhanced conversions, gas liquid separations, and electrochemistry. She's now leading the work on the conversion of CO2 to DME within the E2C project, and we'll discuss the pilot system being built in Petten. So I will hand it over to you, Soraya.
maximize it. Can you see the screen?
Yeah, looks good.
Okay.
Thank you.
Thanks for the introduction, Erin. Indeed, my name is Soraya Sluiter. I'm a project manager at TNO in Patton, and I'm happy to present to you the work and on the development and scale up of the sorption-enhanced DME synthesis technology that we're developing. In short, it's called SETMES, so we'll be referring to that. I will be explaining a bit on the development before the E2C project and also within the E2C project. So a little bit more about the group that I'm working in. There are lots of different TNO units and groups that do a lot of interesting research, and also the group of Delft will be presenting later. But I'm based in Patton, so really on one of the two C's from the Interreg funding agency. And I'm working in a group that's developing technologies for a more sustainable industry. And we're developing these technologies to go towards a CO2 neutral industry. We work on several lines. The first one is industrial heat. The second one is using the energy efficiently, and also working on separation technologies for example, reuse of certain materials. The third line is electrification, including water electrolysis development and testing, for example. And last but not least, we're working on CO2 capture, CO2 storage, and CO2 utilization as well. So within the E2C project, actually, we're working on a combination of all these three last lines that I just mentioned, because we're using hydrogen that's been produced from electrolysis, water electrolysis, and we're doing CO2 utilization by using separation technology as well. So that's also the aim of the E2C project, to produce valuable chemical products by using renewable electricity, for example, from windmills and solar energy. And the target chemical that we're looking at in Patton is the dimethyl ether, or DME. And this is a very interesting chemical. Can be used as a fuel, but it's also a very interesting chemical building block, which can be used to produce other synthetic fuels, but also plastics or other more advanced chemicals, such as aromatics and further on. As a fuel, DME is also very interesting, for example, because it has a very high energy efficiency. The vehicle adjustment is still overseeable, and it's, for example, low toxicity. So this is very interesting fuel, also if you compare it to other renewable fuels. So for now, I would like to move away a little bit from the electrons and go more towards the chemical side and tell you a little bit more about our SETMES technology. Of course, you already had a quick introduction in the movie, and I might refer back to that a couple of times, but I think 5 minutes is quite fast to really grasp the concept and the process. So I'd like to go a bit further into detail in explaining that. So conventionally, DME is made in two steps. The first step is the methanol production. And then in the second step, the methanol is dehydrated to form dimethyl ether. Both of these reactions are limited thermodynamically, which means that you can only get a limited amount, produce limited amount of DME in your reaction, especially if you use CO2, as you can see here. So what we do in the SETMES technology is we add another material, a sorbent, which then absorbs the water that's being formed, and in this way we shift the equilibrium towards the DME side, and this way we can produce DME selectively up to 80% selectively, and also we can use CO2 as a feed instead of CO, as you can see from this graph. So that's really nice. But what you have to understand from this technology is, of course, at one point our sorbent material will be saturated with all the water, and we have to do discharge or a regeneration step for the material. So if we want to produce the DME continuously, we need at least 2 columns. We need several columns, and one will be in the reaction mode, absorbing the water, and one will be discharging the water again until it can go again in the next cycle. Yes, so the main important parameters to have an efficient process is the carbon selectivity towards DME, so a high selectivity towards DME from CO2, and also the productivity. As you can see from this figure, we can increase the productivity by feeding more gas to the reactor. That's this line. But you can also see that there's a trade-off with the carbon selectivity towards DME. So if we have a high productivity, we get a lower carbon selectivity. So this is something that we need to optimize. So we can do that by developing more selective catalysts, a higher capacity sorbent. So these are things on the material development side, but we're also looking into the cycle design. So that was what I was just referring to. The reactor can be in an absorption mode for a certain amount of time, and then we'll have to switch to the regeneration mode. So having several reactors working simultaneously, and for how long and how will the regeneration take place, more this type of process optimization we're also working on, and we refer to a cycle design in that sense. And we're doing this both experimentally developing the process, but also my colleagues are doing a lot of simulation and modeling work on this. So then a little bit about the history of our SETMAS technology. I think we started developing the process well before I joined ECN or TNO in 2014. And we started out more on the material development side and really proving the concept. So that was on a small scale still. In 2017, we did some material screening on this spider reactor. It's called the spider reactor because it has 8 reactors where you can test different materials at the same time. Then in 2018, we went to a bit larger scale, the CATE reactor, where we optimized more the reaction conditions, these type of things. And then in 2019, we continued onwards to the 2-meter high column system. That's 1 column that was also featured in the video that was shown. Here we could also mimic the cycles that the reactor is going through. So both the active, the reaction phase, but also the regeneration can be studied. And then last year only we moved to a multi-column system, which was also showed in the video, the 6-column system, and which is also on a larger scale, so using more or less 30 kilograms of material. And now the next step, of course, is the pilot demonstration, and the pilot for that we're developing within the E2C project. And that will be a large step forward in really demonstrating this technology on the on the larger scale. So a little bit more on the step from the 1 column to the multi-column system, which took place last year within the FLETCH project. We could obtain the expected carbon selectivities as was expected from the modeling and simulation work, but also from the smaller scale experiments. So that was really good news. But what was even more important, we showed that we can use only a pressure swing regeneration. So before we were always considering also a temperature swing regeneration, in which we had to use a higher temperature to regenerate the sorbent material and get rid of the water. But it takes a lot of time because you have to increase the temperature, heat it up, and it also has to cool down. So that takes a significant amount of time, and that thus limits the productivity of your process. But here we tested only a pressure swing, and that was also possible and leading to the similar selectivities. So that was a big step forward. We've also tested for a significant amount of time, more than 300 hours of continuous operation and more than 130 full cycles. And you can see the results over here. We can still obtain high carbon selectivities towards DME. So then the next step is the pilot that's being built in the E2C project. There were a few targets that we wanted to reach with this pilot. The design target for the productivity is the capacity is 3 kilograms an hour of DME production. It's important for us that this is a flexible pilot because it can also be used by other partners. We can move it somewhere else to another location. So that in that sense, we decided to go for a containerized pilot reactor. And of course, we want to show the concept of going from electrons to chemicals in this project. So it should be possible to couple this installation to a electrolyzer. In this sense, we're considering a PEM electrolyzer because we want to go to higher pressures. So that's what we started from. So the design and engineering has been done in-house here at TNO. The building is mainly outsourced. So for the design, we have 3 different containers. One for the reactor system, which is this tall tower. As you can see, there's a little man standing just beside him. So it's quite impressive. And there's one container for the infrastructure, for the pumps and the gases and everything. And there's one container for the analysis of the pilot and also to have the flare here to adhere to the emissions that we can remove here, because at this point we're not looking into the separation of the DME after our reaction yet. So in the design we have 3 reactors in our reactor skid. There's place for a 4th one, but because of budget constraints we only have 3 now. And it has a shell and tube reactor design to take into account heat management. So during the reaction, the oil around the reactors can absorb the heat, and during desorption it can actually provide some heat to the reactors. So only last week the reactor has been finalized at the constructor Bronsberg. So we went there last week. I was myself quite impressed with the entire skid and setup. You can see it over here. It's very difficult to capture as it's really, really tall. And here you can see it on its side. So this will be the large tower containing our reactors and also the reactor materials, the catalyst and the sorbent will be in there. And here you can see the shell and tube design. So there are several tubes in which our materials will be poured and also the gases will be fed through. Then some other pictures of other components that will be part of our pilot unit. This is the flare. So here you can see a hand of a person, and you can see that it's also quite large already. And you should take into account this is a 3 kilogram an hour pilot. So it's yeah, it will only grow probably, but yeah, not as much perhaps. This is the other container that's being filled up at the moment. This is the electrical cabinet for the control system. And here I have a picture of the oil heating system to give you an impression of what the pilot will look like. So along the way in development and scaling up this technology, we have encountered, of course, also a lot of challenges. As a project manager, I can very much relate to some of the organizational challenges that Thijs, I think, mentioned, such as long times that you need for this, high costs that you come across, and also permits, for example. But we've also had some technical challenges. So one that I already mentioned was the optimization between the productivity and the carbon selectivity that we're facing. A lot of work has been put into the cycle design to do this. And something that we now start to also come across is recycling of the different streams. So recycling of your purge gas, for example, how we can do that efficiently. Then, as has also been mentioned, it's also important to always keep in mind the business case and the application of your technology. And this has also been a challenge because there's quite some options in that sense for technology. Where's the feed source coming from, for example, the CO2? That has a large impact on your business case, but also on the technical side. We would like to really go to use industrial gases as well here. Also for the product, we can use DME as a fuel, as a chemical, or even stop at methanol, for example. And all of these different products have their own specs that we have to adhere to, and a different business case for that. Yeah, mentioning the business case, we've also been looking into that, and we recently published a paper on the techno-economic analysis of this power to chemicals ZMS process. And here we have a cost estimate of around €1.30 per kilogram of DME, which this is way above the current market price, which is something like 60 cents. So it's at this point not possible to really compete with the conventional type of production, but we need policies and things to come in here. And also something to work on is probably the cost of the electrolyzer, because we found that this price is mainly dominated by the capex and opex of the PEM electrolyzer. So that's also something that we are looking into within the E2C project. How can we make the electrolysis cheaper? Then other challenges, I think, are corresponding to acceptance, life cycle analysis, and policy. But I think that will be the topic of our next stakeholder meeting, which will take place in May. And I hope to see many of you then again. Yeah, then a little bit about the follow-up of the E2C project and how will we continue with the scale-up. So we did the lab testing at the multi-column system here in Petten last year. The planning is that this summer, over the summer, the pilot will be built up here in Petten. And then in the follow-up project, we will move the pilot container probably to the field lab that you just saw this movie about. And there we will also incorporate the downstream processing, so the separation of the DME, and also do the coupling, the actual coupling to a PEM electrolyzer. And then we would like to investigate further the power to X scale up in case. We will also like to use really CO2 gases from the industry, for example, from a bio-based CO2 gases as well. So at the end of the E2C project, we hope to have a transportable pilot that's specifically geared towards sorption enhanced reactions, and it will be a 3-container pilot. And it will produce approximately 3 kilograms an hour of DME, and it's very efficient in its hydrogen use. That's something I should mention as well. And what we require to produce the DME is hydrogen and CO2. So that's a big plus for the ZMS compared to the conventional DME synthesis, I think, or a PEM electrolyzer, of course, or another electrolyzer, electricity and the CO2 source. So it will be available also to other partners that are interested of testing this technology, for example, with their CO2 stream, or if they are interested to test their catalyst or sorbent material within this pilot, that would also be possible. We're also very interested to look in towards dynamic testing, because if we really want to make use of the of renewable energy, we also have to cope with the intermittent character of this type of energy, and we need to also test our technology for that. So that's something that we're very interested in as well. But I'm also very curious to hear what would be your interest in such a pilot. And because of, for that, we have created a poll in Huva, and I think that Aaron will start it up soon. There will be some questions geared towards this pilot specifically, what type of uses you can envision and think of and would be interested in, but also for the other pilot that will be developed in Delft. And also some questions on what type of model you would like to prefer. Would you like to collaborate within a project, or we have several models in mind for that, and I think Elena will explain a little bit what we have in mind, what options we consider for that in the next presentation. So I'm looking forward to get your input on that, and I think that was my last slide. So thanks a lot for the attention, and looking forward to the questions.
Yeah, thank you very much, Soraya. As Soraya mentioned, there is a poll active. The question regarding this pilot is already active, and the other ones will come active shortly after there's been a little bit more described about the next pilot and the collaboration models. You can see those on the desktop in the to the left of the screen. There's a polls option, or if you're on your phone in the app, then on the home screen you'll also see polls listed. So we do have a few minutes for questions. So I'll give these to you, Soraya. So the first one says, this is Svenne from Witteveen en Bos. Nice presentation, Soraya. Interesting story and good work. It says, from a system integration perspective, I was wondering if it is possible to recycle the water for hydrogen production, and in that way make your system circular. And then there's another question, another part of that, or any ideas on the purity of the water?
Yeah, so that would, I think it's a very interesting question. I've also thought of that myself, of course. I think that will be for the next steps. Ideally, we would like to have a circular system as much as possible. So that's something for future research to definitely look into as well.
Great, thank you. There's a second one. It says, interesting concept. What is the expected footprint of the industrial scale?
The industrial scale, that's a good question. I think maybe send me a separate message and I can look into that a little bit. The University of Sheffield at this moment is doing a footprint, but then a carbon footprint, which I think is also very interesting. But we also need to wait for the results on that. And for the industrial footprint, I'll have to come back to it. Also depends, of course, on the scale of the production, but we can do some quick calculations on that. I don't know it by heart.
Great. I'm sorry, maybe you can put your email address in the chat if
of course,
if you're up for that. I think we'll do time for one more question, and then sorry, maybe you can look in the chat on the Zoom meeting and see the other questions that are coming through.
Of course.
We can do one more here. So it's for the chosen absorption time and feed flow rate, by increasing the amount of absorbent, does it have any characteristic change on DME production rate? And the second part of that is, and what is the optimal ratio of catalyst to adsorbent for maximum efficiency?
Yeah, so we found that this ratio is indeed very important. I forgot to mention that, but indeed there's an optimum in that, having the right amount of catalyst compared to the sorbent material. I don't know by heart, but perhaps Jasper is in the call, and he's a specialist on that. He might be able to answer in the chat what is the preferred ratio. If we can disclose.
Hi, Soraya. Hi, this is Galina here. I can say that we're working with the ratio around 20% of the catalyst fraction. But as I already mentioned in the chat,
fraction.
the catalyst.
Okay, catalyst.
And basically, there is a trade-off between kinetics and equilibrium shift, of course, so you can optimize for each certain case. But in our case, it's 20% catalyst.
Thanks, Galina.
Okay, great. Thank you very much, Soraya.
You're welcome.
Good. So I'm going to give the floor over to the second presentation that's about the activities in the E2C project. This is going to be given by Elena Perez-Galint. Elena has a PhD in electrochemistry from Leiden University and is now a scientific researcher at TNO. Her main activities are related to the electrochemical conversion of CO2 to several added value chemicals, with special attention to integration of CO2 capture technologies and other cost-effective engineering solutions. Elena now leads the work on scaling up direct electrochemical conversion of CO2 to formic acid within the E2C project, and we'll discuss the pilot that's being built in Delft. So Elena, if you want to go ahead and share your screen.
Yes, I'm sharing my screen now. Can you hear me properly?
Yes, we hear you and see you. Thank you.
All right. Okay, thank you, Erin, for your introduction. So I guess I'll go right through the talk. So today I would like to give a brief overview of the activities related to the scale-up of electrochemical CO2 conversion, the challenges we faced, and also the steps we made from lab scale to the industry. So, well, I guess by now we are all aware that CO2 can be used as a carbon source for a wide variety of commodity chemicals like DME, as what I explained, or CO, ethylene, or formic acid. And in the Interreg project, we focus on two chemicals, DME via the indirect route, as Soraya already explained, and then formic acid via the direct route. So in this, and today I will focus on the direct route. So in this direct route, the CO2 is used as the reactant in the electrolyzer, where it's directly converted to formic acid by the addition of electrical energy ideally from renewable sources. So in the E2C Interreg project, the target is to scale up this technology from TRL 3 to TRL 6 and demonstrate the feasibility of producing 1 kilogram an hour of formic acid via electrochemical conversions. So if we zoom up a bit in what I have portrayed here as a black box, so the electrolyzer, we can see the complexity of this. So here from left to right, in the anode, first a molecule of water is split into oxygen and protons. Then those protons cross the membrane that separates the anode from the cathode. And then the protons recombine with the CO2 and the electrons in the cathode to form a wide variety of products. So these products, the product distribution of the reaction, it depends on the electrolysis conditions, such as the potential you apply, the catalyst material, the electrolyte nature, the pH, or the temperature. And yeah, from all the products that can be formed electrochemically in an efficient manner, formic acid is the most viable target molecule from the direct formation from CO2. And this is from an economic perspective. So the production cost per ton of product compared to the market price, but it's also one of the most impactful molecules from a CO2 mitigation perspective. So namely the amount of CO2 that is converted per kilowatt hour. So from this economic analysis, we can also see that oxalic acid is quite a serious alternative, but the market growth potential is rather small, and we expect that oxalic acid will remain a niche application also into the long term. So for that, in this project, we are focused on the formation of formic acid and how to scale up to industrial relevant conditions. So yes, here I portrait the development phases we follow in this project. So in the first part of the project, we started with the material screening, and And here, as it was already explained in the first event of this series, there was a series of developments like the catalyst materials and the structure done by Antwerp University. The gas diffusion electrodes, they were developed by Vito. The type of electrolytes used in the reactor, that they were also developed by the Technical University of Delft. And the reactor configuration that was studied by Tieno. So in this first phase of material screening and reaction optimization, the studies are performed within areas between 1 and 10 square centimeters. And now in this second phase of the project, we are scaling up in 2 stages. So first from 10 square centimeters to 200 or 400 square centimeters. And yeah, we made use of 2 bench scale skids that they are developed and constructed within this project. And then the second stage of this scale-up process is from 100 to 400 square centimeters up to half a square meter electrolyzer. And this last scale-up development will also comprise the upgrading of the electrolyzer from a single cell to a stack. And this stack will have 15 cells units. So yeah, in a couple of slides, I will give more information about these bench scale skids, their functionalities, and also the pilot installation. But before that, I want to briefly highlight some of the challenges. Yes, some of the challenges associated to this scale-up process. So, well, some of the main challenges are associated to the increase of the electrode area. So increasing the electrolyzer area leads to problem, like Thijs was already mentioning, of the mechanical stability of these gas diffusion electrodes and the membranes. It also makes the sealing properties of the reactor more challenging. It can also lead to uneven distribution of the current or uneven distribution of the gas and liquid through the electrolyzer and the electrode. And yeah, also quite important, bigger electrodes lead to higher production of side products like hydrogen, which will harden the safety regulation for bigger setups. And yes, some of the other challenges are associated to the mode of operation. Also, Thijs mentioned this, going from batch reactors to flow or continuous reactor can increase the complexity of the system. So for instance, if we have to control the temperature and the pressure, this whole control, it becomes more difficult. But also to flow reactors, there is associated this non-homogeneity, which can be cumbersome for the efficiency of the electrochemical reaction. And yeah, when scaling up, it's also important to consider the real industrial conditions, and the experimentation should be done at relevant temperatures and pressure conditions. And also Thijs mentioned that this should be done in the early stages. So it's also important to consider the complete process from upstream to downstream, and take into consideration how, for instance, the composition of CO2 source or the presence of impurities might affect the electrochemical process, and how the product is going to be separated and purified from the electrolytic solvent, and also how the side products are going to affect the efficiency of this purification process and things like that. And also we cannot forget that the CO2 conversion reaction is only 1/2 of the reaction. So we also have to consider the anodic reaction in this case and try to valorize it. And yes, as already mentioned, one of the scale-up steps is going from single stack to stack level. And in this development phase, there are some challenges as well. So for instance, with the stacks, the assembly and the maintenance becomes much more difficult. It is also important to consider that during the engineering design of the reactor, that the distribution of the gas and the liquid across every cell in the stack should be homogeneous in order to ensure an efficient operation, that all the cells operates in the same level. And yes, finally, there are also some challenges associated to increasing the current density during the reaction. So if we want to increase the productivity, the current density has to increase as well. But this comes with a price. Yeah, perhaps we lower the selectivity. If we increase the current density, we lower the selectivity, and therefore there is higher side products formation. Or perhaps the catalyst lifetime is shorter, since if we are increasing the current density, the nanoparticles that we normally have in the catalyst, they can detach because of these more harsh conditions we are putting them through. So it's also important to consider all these aspects during the scale-up process. And now I want to show some of the strategies that we use within this project to solve some of these issues I just mentioned. So, for instance, to solve the mechanical stability of the gas diffusion electrodes, Vito employs this casing frame you can see here on the bottom left image. And this casing frame it helps to hold the electrode in place. So it increases the mechanical stability. So, and they can ensure a good stability for electrodes as big as 8,500 square centimeters. Also, both Vito and TNO, we are working on the development of novel type of gas diffusion electrodes with different types of hydrophobic layers on the backside, on the gas side, to avoid the flooding issues, which, right now is one of the most important showstoppers during CO2 conversion reactions when using gas diffusion electrodes, this flooding issues. Another problem associated to increase the area of the electrode is this uneven current distribution across the electrode. So Vito is developing a new type of GDs where the current collector is integrated within the gas diffusion electrode. So it helps to have an even current distribution. Another strategy that TNO we are working in, it's to work with these metallic foams or 3D structures. So on one hand, we increase the active area by having these complex 3D structures. And on the other hand, we also ensure a good connection, electrical connection along the whole length of the electrode. And also the gas and the liquid flows can have an even distribution. And so, for instance, the gas bubbles that they are formed on the electrode or from the side products like hydrogen or CO, they create an insulating layer, which creates a lot of resistance. So there are different strategies to overcome this challenge. So, for instance, at TNO, we have designed and 3D printed different type of flow fields with this type of internal disruptive elements that they help create a more homogeneous flow distribution because they can break the bubbles form. With this type of flow fields with the disruptive elements, we managed to double the efficiency of the electrochemical reaction. Another strategy would be to go towards zero gap configurations. So to avoid this biphasic flow with the coexistence of gases and liquid. And yes, lastly, when thinking about the scaling up an electrochemical reaction, as I already mentioned, it's important to take into account the counter reaction as well. So in order to achieve a better business case, we have to think about valorizing the product form also on the anode. So for that, it's important to consider not only the compatibility of this anodic reaction with the conversion of CO2, because of course it needs to be compatible from a technical point of view, but also we have to take into account that the market size for both molecules should match. So we don't have an excess of one of the products than the other. With this strategy, we can increase the product value per kilowatt hour consumed, and also we can reduce the cost per ton of product formed. Yes, okay, so yeah, to solve all these challenges, we count with a big fleet of setups from a very small scale for fast screening. This is electrolyte volumes of 10 microliters up to 100 liters or so. So in the small scale, we do fast screening, and then we go to bigger scale for process optimization and reaction optimization. And within the Interreg project, we have created 2 bench scale skids and 1 pilot demonstrator. And the first bench scale skid has been designed and constructed by TNO. And yeah, here we can see an overview of the setup, and I'll show you some of the functionalities. So yeah, here this is the CO2 reactant, the potentiostat or the power supply to control the reaction. The whole skid is automated for control and also for monitoring. We count with an online product analysis. And yeah, of course, we have a set of sensors and alarms to operate in a safety manner. And this is the core of the equipment. So we can operate a quite flexible reactor from 100 square centimeters, and we can interchange it for one of 400 square centimeters, and we can have different reactor configurations. It can be operated at high temperatures of up to 85 degrees centigrade and pressures up to 30 bars. And yeah, here you can see all different units for the fluidic system. So where we can control the electrolyte level, the flow, the degree of humidity of the CO2 gas. And yeah, also this kit counts with a pressure equilibration system to ensure the same pressure throughout the whole system. And yeah, this is the second bench scale skid that was designed and built by experts from Vito. So it comes with more or less the same functionalities. So it can be controlled and monitored online. It has a big set of sensors and controllers for the pH, the conductivity, the pressure, flow rate, amongst others. And it also comes with an online gas analysis and a liquid product analysis. And yeah, the most important thing is that the reactor can allocate the gas diffusion electrodes that they are also created at Vito laboratories, and they have surface area of about 400 square centimeters. And yeah, the reason we have created these 2 bench scales is because we have 2 concepts for the formation of formic acid. Is what we call the 3-compartment reactor on the left side, and where here formic acid is formed in situ, inside the reactor. And the second concept is what we call the 2-compartment system, where formate is formed, not formic acid, but formate. So from the process perspective, the 2-compartment electrolyzer needs an additional step for the protonation of formate to formic acid, which makes the downstream process more complex and therefore more costly than the 3-compartment system. However, in the 3-compartment system, the electrolysis is a bit more costly. But if we compare the total cost of both concepts, so summing up the cost associated to the electrolysis and the cost associated to the DSP, we can see in this graph on the top right that in theory they are quite comparable. So that's why we create these 2 bench scales, because we want to investigate experimentally which one is more beneficial. Okay, so these were the 2 bench scale systems, and then we went one step further, and we are designing and constructing a pilot installation that excuse me, that will be able to produce 1 kilogram of formic acid per hour. And yeah, this pilot installation will count with a stack reactor of 15 cells of 400 square centimeter each single cell, So that makes a total area of around 0.6 square meter. And it is designed in a very flexible way, so it can allocate different reactor configurations. It can be integrated with an upstream CO2 absorption unit, and also with a downstream formic acid separation and purification unit. But it also can run independently with pure CO2. And yeah, of course, this will depend on the type of study or research question. The pilot will be fully automated. It will operate in batches with continuous feed and bleed cycles, and it can have 100 hours of unmanned operation. Yeah, it will also count with automated rinsing and washing procedures and an inline sampling system. And yeah, this one can also be operated at high pressures and temperatures, so 30 bars and 85 degrees centigrade. So this pilot installation, together with the pilot of DME synthesis and other units, will be located in the field lab in Rotterdam, which all of it will create the Center of Excellence. And the aim of this Center of Excellence is to boost the collaboration between companies and to strive for innovation. So the idea is that the companies can use these installations for their research. And yeah, now very briefly I want to mention some of the business or collaboration model we are currently setting up. So I just want to highlight that these models are not settled yet. And yeah, we would love to hear from you what would be your ideal model, what type of research you would like to conduct in these installations, and what would be your preference. So yeah, so we have created a poll, as Soraya mentioned, and you can give us feedback about these models, and we would really appreciate that. But yeah, very briefly, these are the 5 models we have in mind of how you, as a company, can interact with these pilots. So the first model is TNO leases the pilot to the customer. So the customer can operate the installation in the field lab, and of course, training can be provided by TNO. The second model is very similar. So TNO will lease the pilots, but the installation can be moved to the customer side. So the benefit is that the pilot can be tested with the real conditions of the process. We have to take in account that if the pilot is moved to the customer side, we need a site acceptance test and maybe some other requirements. The third model is that the customer hires TNO personnel to investigate a certain topic in the pilot. So the pilot can either stay in the field lab or it can also be moved to the customer location. The third model is that the pilot can be sold to the customer. So the customer will have complete control over the pilot. Like for instance, if they want to change certain design aspects or something like that. So this type of model gives more flexibility for the customer to interact with the pilot. And the last model is a collaboration model where the pilot can be used by different partners within a project consortium. So yeah, please fill the poll with your preference and also feel free to suggest another type of model or any ideas you have about this. I think, yeah, with that, I would just like to thank you all for your attention, and I guess we have a couple of minutes for a question, maybe.
Yes. Great. Thank you, Elena. We do have several questions. We can do a couple of them, and then maybe, Elena, you can answer the rest in the Zoom chat.
Sure.
But let me give you the first one. It says, in terms of the business model, which CO2 source would you consider to treat in the first place for the pilot, considering the purity of the CO2 stream, for example, and up and downstream separations?
Yeah, so I think we can consider flue gas, and actually in the next event, they will explain different scenarios and how it changed the business model depending on the CO2 source. So I would encourage you to enroll for the next session in May if you want to know more about how the CO2 source influence the business model.
Great, thank you. We're going to have to go ahead and stop there and move on to the next presentation. But Elena, again, answer in the chat, and
I will.
like even put your email address there that people can contact you afterwards.
Sure.
Great, thank you very much. So now we have a presentation that comes a bit out of the E2C project, but is also a bit more broad than that. So we have Laurens Duplessis, who is a project design engineer at TNO. Laurens has a master's in chemical engineering from the University of Pretoria in South Africa, and subsequently worked for Sasol for 16 years. He's currently contracted by TNO, as mentioned, as a project design engineer to assist on the realization of the pilot demonstrator systems. He will discuss some of the non-technical challenges that come up when constructing and operating the scale of pilots that we have just been discussing. So Laurens, I will give the screen to you.
Thank you, Erin. So just to check again, you can see my screen?
Yep, we see your screen and we hear you. Thank you.
Excellent. So yes, as already mentioned, I'm coming from a bit of a different perspective, being a project engineer. And I was asked to provide a bit more feedback or background, a bit more insight in terms of the so-called non-technical aspects, which was for in scaling up units, which I think was already hinted to in quite a few presentations. So to that, just to set the scene and a bit of a description of where I'm coming from, essentially what we're talking about here is, of course, a scale-up of technology. And really what we are looking at here is then, of course, as was mentioned previously already, you're looking from transitioning from your typical lab scale setups or units and moving through your innovation phase to the more integrated systems and larger scale units or pilot systems, which typically end at having essentially a mini plant situated in an operational environment. So it's really trying to bridge this divide between the research and invention side of things until it is fully realized in the commercial market. To that, of course, what are the typical characteristics? What you find here is during this phase, you see quite a significant ramp up of costs, specifically as you progress from the one demonstration or scale as you move from one stage to the other. And in that, finding money, I think as everybody understands, and I'll probably have some experience to, is getting the funds is quite difficult, to the point where some people has already referred to this as the valley of death for innovation, in terms of having some great ideas, but taking that through, getting the funds and taking it through to the commercial and commercializing it is very difficult. Together that, of course, as well, is as you get more funds, there's probably also a larger expectation from those that are supplying you the funds that the product is going to be commercially viable. So in other words, there's a greater, more firm expectations in terms of actually showing the outcome and getting it to be a bit more of a successful outcome. In that, of course, the research and engineering is also focused on providing further insight into your business case, because it's really all about trying to establish, is there a business case for my commercial market? And to that, of course, then the focus now changes a lot away from perhaps the understanding how the chemicals and all those type of things work. And it's focused more then now on aspects such as scale-up factors. Are you looking at a linear scale-up? Are you looking at some components that might become exponential or stepwise? So to that, needing to understand that, as you already also saw, is that as these pilots become larger, you're also starting to look at the integration, and you sometimes need to integrate different technologies. And then, of course, the other aspect that also receives a lot of attention is aspects of availability and reliability. Typically, industrial type scale units are running for 24/7 or in batches that are longer durations. And to that, you need to start showing that the technology can actually do that, be consistently providing the necessary product that you want within a consistent, with a reasonable uptime. Further to that, of course, another aspect of these type of scale-up units is it's sometimes seen as a demonstration unit or a test bed for future partnerships. And we'll get to that in at a bit later stage. But as you progress the complexity increases, and of course you're always looking to say that at a certain stage it might become more difficult, and you're looking for partnerships to help you to take the technology forward. So that's really what I'm going to talk about. If I speak about this, the scale up of technology, this is really what I'm considering when I want to speak about the scale up of it. So the aim of this discussion, therefore, is to say that as you progress now through these different stages of scale up, you need a bit of a strategic approach that need to consider many things, but the two that I want to talk about is firstly an impact analysis on the execution complexity. And then second to that, combine that then also with your strategic considerations in terms of the commercial viability. So it's really considering those two in concert with each other. And to that, what I would like to do, therefore, is just discuss some of the consideration in terms of execution complexity, or the so-called non-technical aspects associated with scale-up. And again, to that, drilling a bit further down is then within the execution complexity, really focus on three main aspects of execution complexity. Firstly, looking at engineering and design, the aspects associated to that, not necessarily the technical aspects, but aspects associated to how do you execute these things from that perspective. Of course, also then project execution, you need to build these things and you need to take them through a certain design. So to that, there's a project. You usually do this as a project, and there's aspects associated to that. And then one that is sometimes not thought of until you really need it, unfortunately, is the operational support aspect. As you build these things, they need to be supported by somebody from operational side and to take it forward. And hopefully, after I discussed all these, the execution complexity around these three focus points, I will try and show its relation in terms of the execution complexity to the strategic significance of the technology which is that you like to develop. In other words, how does this relate to your commercial viability and sustainability aspects? So in other words, how does the execution complexity relate to the strategic aspects of commercial viability and sustainability? So firstly, let's then consider the engineering and design requirements or the issues associated with that. And the way I would like to present this is first, let's just consider what do you typically see with these type of lab scale unit or units during the scale up exercise or the scale up, taking the scale up and design of the technology. And in that, it's really a spectrum of different sized units. So I thought what I'll do is just try and describe the two end states. One state being, or the beginning is being the lab scale size, and then of course looking right up to the pilot scale or industrial pilot scale size on the other side. And what you find then is, in terms of lab scale analysis, the focus is pretty much from engineering side on equipment specification and buying those as a lump sum, with maybe some small auxiliaries to ensure that that they get the necessary things that they need to be able to operate. And then from there, you move on to, if you look at the larger scale units in terms of a full integration of subsystems and equipment. So you're actually moving away from buying equipment to almost buying an integrated setup. And to that, there's some aspects associated to engineering that needs to be considered. Other aspect is also looking at the lab scale or lab scale units. You are still looking for a lot of flexibility in your design. You still not exactly sure how you want to take it forward, and you want to make sure that you've got some option to research different things. Whereas if you really look at the large scale units, the expectations in terms of what it is that you're going to build and what it is that you're going to deliver are very specific. So the engineering outcomes becomes, as you move through the scale up phases, becomes more and more defined and more predefined. In that also, of course, as you need to build larger and larger scale-up units and must be able to show the engineering outcome, your resourcing changes. So where you start off with maybe a few specific or discipline-specific resources that maybe knows the technology well, as you scale through the technology, of course, you are looking to larger and larger, and ultimately can be a full multidiscipline engineering team that supports a project manager. And if the team really gets large, you can even look at engineering management. So really large integrated teams that you need to do. So what are the key things that you need to consider when assessing the complexity of your engineering design? And of course, because of the expectations in terms of the certainty, due to the increase in cost, you need to achieve certain outcomes. Of course, nobody's going to give you a large amount of money and just not expect something from it. So, and the more money they give you, the more you need to be able to show. what you've done with that money. So to that, that necessarily requires a specialized input and larger teams. You need to be more sure of what you say. And further to that, of course, to that, a further expectation in terms of more oversight, more hold and witness, more points, more checks as the funds that is being provided, as the expectations associated to the outcomes becomes more and more specific. Further to that, of course, as you progress through the different technology stages, there's also aspects associated to the complexity and the need for integration, which will require additional engineering effort. And one that has already been identified or discussed was the increased requirements for automation, where perhaps started with a system where automation is really only about data logging or capturing some information, such that you can understand what is really happening. Automation becomes something that is actually a critical part of your control stability, ensuring that you have stable operations as you build these larger and larger units, as a specific example. And further to that, with larger volumes, of course, also comes more and more stringent safety requirements. So the tolerance for safety doesn't change throughout the scale up, but definitely the impact associated to that becomes a lot larger. And to that, of course, what you'll then find is that it's not, you need to show more and more, not only prove good engineering practice, or show, or as you continue in building these larger units, there's expectation that you prove your good engineering practice by means of third-party verification. An example, again, if looking at something like the pressure equipment directives or anything like that, what you'll find is that for smaller volume vessels, for smaller units, they will indicate typically that comply to the best practice, design practice, but as you move to the larger units or larger volume vessels, the expectations are now you need to get inspectors in, they need to certify the design and review and make sure that everything is okay. And again, as I just said, more safety brings in more responsibility, more risk, and to that you will have to have more formalized internal review and witness points. Larger HAZOPs, pre-startup safety reviews, we'll get to that just now, but all these things just compound the aspects associated to this. Then there's, of course, your project execution requirements. And to that, again, what you're looking at during your lab scale analysis, it's a fairly flexible execution strategy. You're fairly open to allow the what it is that you want to build and to ensure that you've got some flexibility. But as more and more money comes through, as you're scaling up these units, there's more and more expectations in terms of having predefined quality management plans, schedules, and budgets. The boring things, but the things that I find interesting, unfortunately. Further to that, of course, starting off a few generalist resources, you move on to more larger specialist teams that need to support the project manager, engineering manager. So you're sitting with a different type of skill set between the two different ones. And then your procurement strategy also looks a lot different, where in the smaller scale units, you're looking at more lump sum procurement of equipment. You can look at full-on, phased engineering contracts, not only buying equipment, but you have service contracts and the like, and construction contracts which you need to manage. So it looks completely different as you progress forward. So again, what are the key considerations? You need to consider project value and combination of the complexity. Of course, there's aspects associated to the integration requirements. When looking at complexity of your projects, you need to consider how many different technologies are it that you're trying to combine, the number and expectation of role players and stakeholders. The more stakeholders you have, the more overhead you need to, you're going to spend to ensure that you keep everybody abreast of what it is that they need to know and make sure that you manage those expectations. And of course, you have got more complex contracting strategies. Associated with that, of course, is also on this other side, the expectations in terms of timelines and budgets. More, as I already mentioned a few times, more funds require more certain outcome. And second to that, as people see that there's a gap within the market to actually fulfill, which this technology can fulfill, there will be more and more pressure to get this to market so that you can fill that gap before somebody else might fill it. Then lastly, operational support requirements. Again, what you look at here from operational support in terms of large scale is really just a few individuals with relatively little in terms of procedural hold points in handing over to somebody, or it's probably the scientists themselves that are actually managing or working with the setup. You will get to a very formalized procedure of hold and handover process, safety reviews, dedicated commissioning teams for the larger scale units. Then also considering aspects of logistics, you've got fairly relatively little to worry about in terms of lab scale or smaller scale units. But if you start making a lot of product, have larger volumes, you need to consider supply contracts. Marketing teams might start being interested because they're looking for opportunities in the market. And of course, with all this comes operating budgets. Then
Excuse me, Lawrence, I hate to interrupt you, but it looks like the sound is not working. It looks like we're having sound problems. But it looks like Lawrence cannot hear me to do that. But it looks like the presentation's almost over. Sorry about this, everyone. It looks like we're still having sound problems. Can anybody type in the chat if you hear me? I don't know how far the sound problem goes. Okay, great, thank you. So unfortunately, I think I have to let Lawrence finish and then we will get to the next presentation. He doesn't seem to hear us. So Lawrence, it looks like we don't hear you and I don't know if you hear us. So we're going to have to continue to the next presentation. Sorry, we don't hear you.
Can you hear me now?
Yes, we hear somebody.
Can you hear me already?
Still not hear me?
Yes. Oh, yep. There you are, Lawrence.
Hi.
Lawrence, did you? No. Okay. Well, we're going to have to go on to the next presentation, which is actually less of a presentation, but something that I'm quite looking forward to.
I can hear you now again, Erin.
Oh, okay, great. So Lawrence, if that was you, it was just the last couple of minutes just cut out all of a sudden.
Oh, sorry for that.
Yeah, but we did get most of your presentation, of course. We do need to move on.
A couple of minutes was brilliant, by the way.
Yeah, the best of the presentation, I'm sure. So, if you're back online, why don't we, why don't I give you one question really quick and then we will move on to the next thing. So we had one question come in. It says, do you think there will be a special safety integrity level protocols while working with suppliers and special ISO standards to be created for CO2 electrolysis? Or can we use the current regulations at the moment?
Yeah, it's a bit of a tricky question, but if I consider safety, integrity levels and the like, I think there are, these days, if you look at the norms and specifications, they are becoming what we call more outcomes based. In other words, they're not as specific to the technology, but more focused on setting certain outcomes, and you need to prove those outcomes. So in that, the specifications are becoming more and more flexible, and to that, I would not expect a lot of adaptation is really needed. If I look at what we are starting to deal with in terms of pressure, temperature, those type of things, they still stay the same, even for electrolysis unit. So I would say a lot of it will be able to accommodate, and there might be one or two tweaks that you need here and there, but I don't think there's a large scale need for a lot of changes in terms of laws.
Great, thank you so much. You might look in the chat, Lawrence, and see if there's maybe some other questions coming in that you can answer. If you do have questions for Lawrence, please type them in there. And then let's go ahead and move on to the virtual tour of the electrolyzer testing station at Tino in Petten. So I will give it over to Soraya, who will lead the tour.
Okay. Hello, everyone. Hi again. Can you see me?
Yes, there we go. You should be visible for everyone now.
Okay, great. Well, nice to see you again. I invited my colleague Hans to show you around in the Faraday lab.
Hello.
And he's in charge of the PEM stations and a real expert on that. So we will show you in this live virtual tour. So let's go to the lab.
Okay. Thank you, Soraya, for this introduction. We first start here in the operator room for our PEM stations. It's a separate room from the test hall. It's a bit more quiet here, and you can do all the controls on the screens here. All our systems can run 24/7 without supervision. It's all very safe, and in that way we can also do long-term testing if we want to. So let's have a look in the experimental hall. This is our new experimental hall. We call it the Faraday lab. It's around 200 square meters where we have availability for test stations. And it's now divided in two groups. We have our PEM stations for low temperature, and we also have a department for high temperature test stations. And of course, the new alkaline station. So let's walk on. We have facilities for gas analysis, of course. So there we have the part for the low temperature PEM electrolysis stations. And over here we have the part for our SU high temperature solid oxide test stations. And here we have a row in total 6 PEM electrolyzer stations. And this is one of them actually running now. We're able to do testing more on the small scale. And the maximum pressure for hydrogen on the cathode side is then 100 100 bars, and on the anode side, the oxygen side, 10 bars. So we can go to quite high temperatures. It's more or less for smaller setups. Let's say regular around 10 square centimeters or 25 square centimeters. We have the capability of controlling the temperature very well. So the temperature of the stack is not controlled by the demi water as an input, but we can really control the temperature on a very detailed. It has separations in the test rigs to separate the water and the gas afterwards. We can measure the flows that go in and go out. Temperature measurements, of course. We can do different kind of testing, all in programs if you want to, for long-term testing, different temperature conditions, but also for kind of simulation of what happens when you have your feet off the stack with, for instance, solar panels or wind energy. So we can do a cycling mode. It's all very compact test stations, and it can run, as I said before, 24/7 without supervision. We have a gas detection inside in case of leakage, which will shut down the systems. High temperatures alarms also will shut down the system and put it in a safe mode. So as I said, we have 6 stations of those, so we can do similar testing. If we have a question from a client for different kind of more cells to test on the same conditions, or more cells under different kind of condition, can all be tested in parallel. We go a bit further, can have a look more in detail, of course, if you want. So you on the right hand side here, I can open the box to make it more clear. On the left side here, you have the inlet of water on the anode side of the cell. And here behind, you have the outlet of the water with the produced oxygen, of course. That's all done in plastic tubing because it's quite low pressure at maximum 10 bars. On the other side, you will have, of course, on the other side of the membrane, you will have the hydrogen production with a little bit of water. That's all in stainless steel because it has to resist 100 bar pressure. Of course, we can also go on lower pressures. It's anything from the range between the 2 bars until 100 bars. We have a EVM boost here. That's to set a load on the stack. But also we can do impedance measurements to look at local resistance of the cell. Okay.
Is now a good time to do questions? Or? So we have one question coming in.
Yes.
Have you tested intermittent conditions, and what kind of issues have you detected? Do you have any advice on that, perchance?
Sorry, can you repeat that? Intermittent conditions?
Yeah, intermittent conditions. Have you tested those, and what kinds of issues have you detected, or what kinds of advice would you have?
Yeah, okay. You mean cycling, let's say having a load on for a few minutes or hours, then having the load off, having the load on again, a cycling mode, that's what you mean?
I think so.
Yes, okay. Yes, we did those kind of testing. It's not a big problem, but the system, you cannot go really off load totally. So you always need a little bit of load to keep the system running, because by having the load, you also build up gas pressure, and the system needs a bit of internal pressure to function very well. But so that's more a technical thing of the installation. But for the test condition, there's no problem there. No, we have been doing those kind of testing, and yeah, we can do those kind of cycling mode in having different currents, current on and off. But also you can do temperature cycling if you want to.
Okay, great. Are there any other questions regarding these PEM testing stations? Feel free to put it in the chat, or if you want to unmute and us directly, feel free to do that.
Yeah, I would like to ask Hans a question. Can you hear me?
Yes, go ahead.
Oh, great. Hi, Hans. Thank you for showing us the test stations. And you mentioned that you are testing different sizes of cells. I would be curious, what type of challenges do you see when you go from the 10 square centimeters to 250 or higher?
Yeah, 250 is quite big. These test stations are what we tested at the most is 100 square centimeter. So a 10 by 10 cell or 10 by 10 centimeters. Or we can also go to very small cells. So that's about the range where we can test, or even a possibility with a very small stack, 2-3 cells. Those are that's what the test stations are designed for. Yeah, what do you? There are technically there are not really problems with that, as long as you are within the range that you have the maximum amount of power that you want to put on the cell. So the load per square centimeter is within the scope of the test station. Technically, it doesn't make a lot of difference. There are not many, no, there are not more problems if you test a small cell or a big cell. And right now we also had a new test station. In the beginning when we came in, Soraya had it on the video. That's actually a station where we have 8 very small cells. That's based on a square centimeter cell, where you can do a very fast scanning of cells under the same conditions, and do a multiply of cells, because based on one test result, it's not really a test result, we say. So does that answer the question?
Yes, so it sounds very promising that you can get the same performance in different sizes. And I was wondering if you are looking into the different components, membranes, electrodes, and in this longer testing, which is typically the part of the electrolyzer that you have problems with the lifetime, that degrades faster. Would you say it's the electrode, the membranes? What is your experience?
Oh, yeah, that's hard to say. That really differs from cell to cell. We also make cells ourselves. And to be honest, I'm more into the technical side of the test station. So I'm not doing a lot of testing myself. So we have other colleagues for that. So yeah, if you want to know more about results, then I can ask, or you better ask other colleagues of mine. That's really about the testing. To me, I'm more the technician in the lab here, and yeah, trying to make the testing as good and reliable as possible.
Yes, thank you very much, Hans.
Okay, you're welcome.
Great. I think we have time for one more quick question here, and then we should probably move on to the next station.
Yes.
Do you monitor crossover of gas, H2 or hydrogen and oxygen?
Yes, we do. Yeah, we have built-in sensors to monitor the amount of crossover. So that's on really inside the system. We monitor there, and but that's not very precise measurement. We more use it for safety. So if the amount of hydrogen and oxygen, for example, is above the 4% limit, then we shut down the system, because it's to avoid any internal explosion. For the more precise measurements, we have our gas analysis apparatus, which is really accurate to also find very low crossovers of hydrogen and oxygen in hydrogen. So every test station is connected to the DC, and we can also automate the DC measurements through all our stations, even also on a 24/7 basis. So we can always monitor what is happening with all our stations.
Great, thank you.
Right. Okay. And I will now give the sound to my colleague Raghu.
Yep. Hi. My name is Raghu Samaraju. Yeah, I'm a colleague of Hans. He's actually the manager of this lab. He's also working. He has a lot of experience here, and I'm, let's say, pretty new, maybe 2 years now working here. But yeah, I'll now show you the alkaline test station. So yeah, this is basically an alkaline test station, which compared to our PEM stations, much larger, much bigger. But yeah, we here, this is in-house developed, let's say. The engineering and the construction, everything is done by us. But this station is partly funded by Faraday Lab and partly by the E2C project. So what we do here is, this installation is still under construction. Let's say we're still commissioning phase. So we received the cells from University of Exeter. They made this anion exchange membrane cells in 10 by 10 and 3 by 10 centimeters square and 100 centimeters square cells. So we received them. So we have to still commission the system, and then we try to fix the whole thing and try to test it. Yeah, basically this could be the maximum right now. How can I say it? That the maximum capacity is 100 centimeters square right now. But yeah, we could still go to a higher, let's say, surface area cells. But right now the scope is only 100 centimeters square max. So why we use alkaline or the anion exchange membrane cells is because we wanted to be more competitive. Let's say we want to make, these are at very low TRLs, and then we want to make these electrolyzers to at least to PEM level, let's say. Yeah, but it still needs a lot of research and a lot of effort to be put in. But yeah, we are getting there. In this project, hopefully we do something which could be useful in the follow-up projects. Then we can have more testing done. And why alkaline? Because they are more, or anion exchange membrane, they are more cheaper materials, and the catalysts are much cheaper compared to the PEM cells. That's from my side. Any questions?
I don't see any questions coming through quite yet. Feel free to type, anyone, or feel free to unmute and ask directly.
I would like to ask you something, Raghu. Thank you for showing us this impressive installation. Now I'm curious, let's say if in the project there were of course cells developed especially for testing in this station, but how flexible is this station to test other reactors? Let's say if somebody comes to you with a reactor or with a particular electrode to test in this station, how flexible it is for this type of questions?
Yeah, actually we are open to that. We are actually, it's not only because right now we are still developing. We got these cells from Exeter right now, but we are open for anyone who want to test their electrodes or test their membranes or test their cells. We are quite open, and then we could fix it in, and then we could try to test it. Right now, that's the idea of this station.
Is it also capable of reaching different temperatures or pressures like as the PEM cells, or?
The scope of the installation right now is this whole installation is built for maximum of 30 bar of hydrogen and a maximum temperature of 90 degrees. And the flow rates you can use approximately 3 liters per minute.
Yeah, so that gives quite a range for testing, it seems.
Yes.
Yes.
Exactly.
Yeah. So you would be able to replicate quite realistic industrial conditions with this station.
Hopefully, yes.
And is the area of the electrode limited to the 100 square centimeters that you said, or could you test larger size electrodes?
Yeah, basically we are in such a low TRLs. Also, we have to really do the lower surface area cells, to be honest, understand what's really happening by doing some sort of, we are also developing this, lifetime testing and accelerated stress test to see how the module and the things behave, because this is completely new for us. This is this is very unique, compared to that of the PEM cells. So we have to see how does it behave and gain some knowledge and try depending on that, we can really go forward.
Yes, thank you very much.
Yeah, thanks.
Thank you very much. There were a couple other questions about the differences between the AEM and the PEM installations, and also about the conditions of this installation. I believe you answered those, but is there anything else to add to that?
Basically, this installation is not only for anion exchange membranes test station, but also the alkaline. So you could switch between alkaline phase and the anion exchange membranes. But for the PEM, probably you have to use a different type of, let's say, feeder. Here we use caustic as your feed, but in the PEM station you have a feed of pure water. So that's only a difference between the PEM and the alkaline right now. But yeah, we have to do a lot more.
Okay, great. Is it possible to get an up-close view of this one as well, or is that too confidential?
There is no cell right now, but it's just the setup.
Okay.
We don't have a cell yet. We didn't mount the cell yet because still in the commissioning phase. We are looking and fixing the things. It was just delivered to us last week, so we are trying to test the software. And, unlike the PEM cells, we wanted to really have it like running unmanned 24/7. So we are still working on it.
Okay, so the cells will go here, it looks like.
Yeah, the cell comes here. Exactly, the cell comes here, and all the lines are here. So the cell will come here. So this is the area what we have. So if you have a big, something like 15 by 15 centimeters, it still goes in.
Okay, great. Perfect. Okay, well, I think that's about all the time we have. We're going to go ahead and wrap up the event now. But thank you very much for the tour. It was very great to see, and a good
thank you.
Replacement for being in person. Thank you both very much.
Yep. Bye-bye.
Bye. Thank you. Good. So I'm just going to put my screen up again. Great. So just to wrap it up really quick, I will hand it over to Anka one more time to give the official closure, but I just wanted to give a couple logistics things. First, from my side, thank you very much for your participation and joining us today. So just like there was the coffee break, we'll have an opportunity for networking. I know some of the speakers will join the virtual meetup, they're called, at the end of the event. In order to find that again, please just go to the community tab. Then you'll see meetups and virtual meets, box that you can click on, and then there's a meetup for post-event networking. There's also several live polls within the Hoover app as well. These you can find to the left under additional resources under the or in the desktop app, and just from the home screen if you're on your phone. This is asking for input regarding the pilot systems that were presented today, and how you might like to use the pilots, or what a collaboration model could look like. And then as well as just a little bit of feedback about the event in general. So we'd really appreciate you taking a moment and to fill those out before you sign off. If you have any other feedback, please feel free to leave that in the chat, in the discussion topics. Feel free to message me directly. And then I'll also be sending out just a follow-up email following this event that will give you a link that you can watch the recording. And also there'll be a post-event survey that would also be great if you could fill in. And so just to make sure you can find the polls, okay, this is the desktop app version, and there's just a box here, and you can go through each of the polls and submit your answers there. So that's all from my side. Again, thank you very much. I will hand it back over to Anka. Anka, go ahead.
Yes. Thank you very much, Erin, and thank you all for staying with us through this event. This concludes our second event in a series of 3 events. A few weeks back, we have presented you the advancements from the project on materials, and today we have walked you through the development of infrastructure that we are addressing in the project, and we have learned from from electrolysis experts how it looks when electrolysis processes are being scaled up and what challenges are there. What I would like to also share with you is that you can stay in touch with us for the project in general. You can sign up for our newsletter or follow us on Twitter and on our LinkedIn page. If you want to be more involved with the project, there is also a possibility to become an observer partner of the project. And then you will be invited to extra events where the projects of the results of the projects are being presented to you. Another thing that it's specifically addressed to the students and the postdocs. We have a winter school organized in February of next year. We are aiming for a face-to-face event. It will be organized by the University of Antwerp and the University of Exeter. Yeah, our wish is to make it face-to-face, and we hope that will be possible by that time. I hope to see most of you there if you're postdocs or PhD students. Yes, the next one. Thank you very much. And before ending, I'd like to invite you to the third event in this series of 3 events, where we are going to look at how to bring Power to X to life. It is connecting technologies and sectors, and my colleagues from the project are going to talk about the roadmap and the business cases for the different technology lines that we are looking at. I hope to see you there and to get input from you there. And with this, thank you, Erin, for organizing this event, and I thank my colleagues for their lectures, and of course also our keynote speakers. Now, I hope you'll have a nice evening, and let's keep in touch.
Great. Thank you, Anka. Thank you, everyone.